Hey everyone, and welcome back. We're diving into something you requested, sliding windows.
Yeah.
This is a really cool algorithmic technique for efficiently analyzing data.
It is a neat one, and you know what? It's a lot like scanning a page looking for a specific keyword.
Right.
You didn't read the entire page again each time, right?
You focus on a chunk and then slide along.
Exactly. So in this deep dive, we're going to see how that same concept can be used to solve some pretty tricky problems in programming. And of course, we have an expert here to help break it all down.
Well, what's really fascinating about this technique is how it helps you find those patterns
Mm-hmm.
and even solutions without getting completely bogged down by how much information you have.
Right. So you've given us some code snippets and notes, which is awesome. We really appreciate that.
Yeah.
And you seem really curious about how these sliding windows can help with all sorts of different problems. So should we just jump right into it? Absolutely. Let's kick things off with a classic problem, the one you highlighted in your notes, finding the longest substring without repeating characters.
Oh, that's a good one.
It's a very common one. Leak code problem number 3. You often see this in coding interviews.
Yeah, okay, so let's break that down a bit. Imagine you have a string of characters, and you need to find the longest sequence within it where no character repeats. I can already see how a brute force approach, where you just check every single substring, would be a nightmare.
It would be incredibly inefficient, especially if you're dealing with a really long string.
Right.
That's where this sliding window technique really comes in handy.
So how does it help?
Well, instead of checking every single combination, you're essentially creating a window that slides across your string.
Okay.
And we use a dictionary to keep track of the characters we've already seen inside that window. Think of it like our character tracker.
Yeah, I'm picturing this window moving across the string.
Uh-huh.
What happens when it encounters a character that's already in our dictionary that we've seen before?
That's where the magic happens. If our window bumps into a duplicate character, it means that particular substring isn't unique anymore.
Okay.
So we start shrinking the window from the left side, removing characters until we get rid of that duplicate.
Oh.
But the whole time, we're keeping track of the window size because the largest window we encounter, that's our solution. That's the longest unique substring.
So it's like a constant dance between expanding the window to explore new characters
Yeah,
and then shrinking it to make sure we only have unique characters inside.
exactly. And that's what makes it so efficient. Instead of checking every single possibility, we're strategically adjusting this window.
Right.
So we only focus on the promising areas of our string.
And I'm seeing how the Python code you provided does this. It's like the dictionary is the memory of our window,
Yeah.
telling us, hey, you've seen this character before, time to adjust.
Exactly. And by using this approach, we can solve the problem in what we call linear time. And in terms of that big O notation, it means the time it takes to solve the problem only grows in a manageable way, even if you have a massive amount of data.
That's a big win. All right, this is starting to make sense. But is this just a one-trick pony? Can sliding windows handle more than just these unique substring problems?
Oh, absolutely not. This is just the tip of the iceberg. The real beauty of the sliding window technique is how adaptable it is.
Okay.
And you actually highlighted a few other leak code problems in your notes that show this off really well, like finding the longest substring with at most 2 distinct characters, that's problem 159, or finding the smallest subarray with a sum that's greater than or equal to a target value, that's problem 209.
Okay, so the core idea, the sliding window, stays the same. But we tweak how we're moving it and what makes it expand or shrink, depending on the specific problem, right?
Exactly. It's like having this flexible tool in your toolkit that you can customize for different tasks. But now, why don't we dive into another problem that you highlighted, finding anagrams within a string? This one gets a bit trickier, but it still relies on that core sliding window principle.
All right, anagrams. That's where you have words with the same letters, but rearranged, like silent and listen.
Exactly. So we're not just looking for an exact match, we're looking for those rearranged versions hiding within a larger string.
Right.
So how do we do it? Well, instead of just checking for an exact match, we got to focus on how many times each letter appears.
Okay.
And we use a really handy Python tool called Counter to do just that.
Counter. It's like a
Yeah.
dictionary that tells you how many times each element shows up.
Yeah, got it. So we use Counter to create these frequency dictionaries, both for the pattern string we're searching for and for the sliding window itself.
So we're basically comparing these two dictionaries to see if they contain the same characters with the same frequencies.
You're catching on quickly. Now, the code that you sent us, it introduces a matches variable to track how many characters in the window actually match the frequency in our target pattern. And if all the counts line up, boom, we found an anagram.
Okay, so the window is moving along, constantly comparing its own frequencies to the pattern's frequencies.
Precisely.
That seems pretty intricate to manage.
It does require careful bookkeeping,
Mm-hmm.
but that's the beauty of the code you provided. It manages the window's movement and these frequency checks very carefully, making sure we don't miss any potential anagrams while staying efficient.
So it seems like the key takeaway here is that it's all about defining the rules of the game for our sliding window.
Yeah.
We tell it how to move, what to look for, and how to adapt based on what it finds.
Exactly. Which brings us to an even trickier challenge you pointed out. Finding the minimum window substring.
Okay.
Imagine we've got a target string and a much larger string. We need to find the absolute smallest part of that larger string that contains all the characters from our target string.
So it's kind of like the anagram problem. But now we're not just looking for any match.
Right.
We want the most compact match we can get.
Exactly.
Okay, I'm intrigued. How do we approach this one?
Well, the code you sent over uses two dictionaries, map0 to store the target string's character frequencies, and win to track the frequencies within our sliding window. Then we have these counters, have and need,
Okay.
which help us manage the logic.
So if I'm understanding this right, have tells us how many of the target characters we've got in our window at any given moment,
Yes.
and need represents the total number of unique characters in that target string.
Precisely. So our window, it keeps expanding until have matches need, meaning we've captured all those target characters,
Okay.
but then we get clever, we try to shrink the window from the left.
Right, to make it as small as possible.
Exactly, to see if we can make it even smaller while still containing all those target characters.
Mm.
We're trying to find that sweet spot, the absolute smallest window that fits the bill.
So we're trimming the edges, seeing just how compact we can make it without losing any of those essential characters.
Exactly. And what if we accidentally shrink too much and lose a crucial character? Well, we just expand again.
Okay.
It's this constant back and forth to find that perfect balance.
Right, make sure we have all the pieces, but the window is as small as it can possibly be.
Exactly. And the code keeps track of the smallest window we found along the way. So in the end, we've got that most efficient solution.
I'm really starting to see how these seemingly simple window adjustments can lead to such elegant solutions.
Absolutely.
This is pretty impressive.
It is, and believe it or not, we've only scratched the surface. Sliding windows can handle so much more than just substring problems.
Really?
You also highlighted a problem that's all about finding the maximum value in a sliding window of a fixed size.
Okay, so now we're shifting gears a bit,
Yeah.
focusing on numerical values instead of characters.
Exactly. So instead of matching characters, we're looking for the biggest number within each window. And for this one, we bring in another tool, the deck, or double-ended queue.
Deck, right, I remember those. They let you add and remove elements from both ends of a list, don't they?
They do.
But how does that help us find the maximum value?
Imagine our deck as a leaderboard for the window.
Okay.
As the window slides along, we add the new element to the deck.
Right.
But here's the key. We also remove elements from the other end to keep the deck sorted, with the maximum value always at the front.
So it's like a self-updating leaderboard that always shows us the current champion within our window.
Exactly. And this technique is incredibly practical. Think of things like tracking stock prices,
Oh, yeah.
or maybe sensor data.
Mm-hmm.
You can use this to constantly monitor the highest value within a moving time frame.
So we've gone from finding substrings to pinpointing anagrams and even analyzing trends.
You got it.
I'm seriously impressed by how much we can do with this simple concept of a sliding window.
There's a lot more to come. You also flagged an interesting problem in your notes, counting subarrays, where the product of the numbers is less than some given value, okay? That's LeetCode problem 713. This one shows a subtle but crucial difference in how we manage the sliding window.
All right, so now we're multiplying numbers within the window
Yeah.
instead of adding them. What changes?
It changes how we move the left edge of our window.
Okay.
In many sliding window problems, you might move the left edge back and forth to adjust the window size.
Right.
But with this specific problem, the left edge never moves backwards. It only goes forward.
Wait, so we're not shrinking the window from the left like we did before?
Nope.
Are we sure we're not missing potential subarrays by doing that?
It might seem strange at first, but it makes sense because of what we're trying to find.
Okay.
We only want subarrays where the product is strictly less than k. So once we've found a subarray that works,
Mm-hmm.
any subarray extending to the left will also have a product less than k. Moving that left edge back would just be repeating ourselves, basically.
Right. It's like we're building a chain, and once we find a valid link, we can just keep extending it to the right, knowing all the links to the left are already good.
That's a great way to put it.
This feels so different from the earlier examples where we were adjusting the window on both sides.
It is different. In this case, the left edge is a one-way street. It just keeps moving forward to discover new valid subrays.
This is blowing my mind. I never knew there could be so many variations in how we manage that sliding window. It's not just about moving a window of a fixed size. It's about understanding the problem and adjusting the window's behavior to match.
You got it. And that's what makes this technique so powerful. It's not a rigid formula. It's more like a flexible framework that you can adapt and fine-tune for all sorts of problems.
I'm loving this. So are we ready for the next challenge? What else can we do with sliding windows?
Absolutely. Buckle up, because we're about to step into the world of line sweep techniques, and they're fascinatingly connected to sliding windows.
Ooh, line sweep. That sounds intriguing.
It is. And then later on, we'll even see how sliding windows can team up with another powerful concept dynamic programming to unlock even more elegant solutions.
I can't wait. This is going to be awesome.
I think so too.
All right, everyone, stay tuned. We'll be right back after a short break.
See you soon.
All right, so we've covered some ground with sliding windows. We've seen how they can be used for all sorts of string and array problems, from finding those unique substrings to spotting anagrams and even figuring out maximum values within a window. I'm really starting to see how powerful this technique can be. But what other kinds of problems can sliding windows help us with? You mentioned something called line sweep earlier. What's that all about?
Line sweep is a really interesting application of the sliding window idea. But instead of sliding across like a string or an array, we're sweeping across a timeline, like you might see with the schedule.
Okay.
Imagine you have a bunch of events, like meetings, each with a start and end time.
So now, instead of characters or numbers, we're dealing with these intervals on a timeline.
Yeah.
What's the advantage of using a sliding window in this context?
Well, think of it like this. Our window, it's actually a point that's moving along that timeline.
Okay.
As it sweeps across, it hits these start and end events, almost like it's scanning for those critical moments. And by keeping track of which events are active at any given point, we can answer all sorts of questions about the intervals.
So it's not so much about finding a specific pattern within the window.
Right.
It's more about understanding the state of things, what's happening as our point moves through time. You mentioned a leak code problem, number 252, that uses this line sweep technique.
Yeah.
What's the challenge in that one?
The challenge is figuring out if a person can actually attend all the meetings in a given schedule.
Okay.
And Line Sweep offers a really elegant solution. First, we sort all those meetings based on their start times.
So we're arranging the timeline from the earliest meeting to the latest.
Exactly. And then our window, that point in time I mentioned, sweeps through those sorted meetings.
Right.
And the key here is, as we encounter each meeting, we check if its end time overlaps with the start time of the next meeting.
So if there's any overlap at all, that means the person can't be in two places at once.
Right.
So they can't attend all the meetings.
Precisely. It's a very intuitive way to approach the problem and come up with an efficient solution.
That's really cool. And there's another related leak code problem, number 253, where we have to figure out the minimum number of rooms needed to accommodate all the meetings without any conflicts, right?
That's right.
How does Line Sweep help us there?
It's a little more complex, but the logic is still pretty straightforward. As our point in time sweeps across that timeline, we're going to use a counter. Every time we hit a meeting start, we increase the counter.
Okay.
Someone just walked into a meeting room, right?
Mm-hmm.
And every time a meeting ends, we decrease the counter. A room just freed up.
So the highest value our counter ever reaches.
Ah,
That tells us the maximum number of meeting rooms that were ever in use at the same time,
exactly.
which means that's the minimum number of rooms we need to handle the entire schedule without any conflicts.
Precisely. It's a clever way to see how those meetings flow throughout the day and where we might have those bottlenecks.
This is awesome. It's like we're not just analyzing the data within a window anymore. We're simulating a whole process as it unfolds over time.
Exactly.
This line sweep idea is really cool, but can you give me some real-world examples where we'd see sliding windows or this line sweep technique in action outside of these coding challenges?
Absolutely. Think about analyzing stock prices over time. You could use a sliding window to calculate moving averages, which helps to smooth out those price fluctuations and identify trends.
Okay.
It's like a window moving across a price chart, continuously giving you a summary of what happened in that specific time frame.
Right. So instead of being distracted by all those daily ups and downs, we get a clearer picture of what's happening overall.
Exactly. Or let's say you're dealing with data from sensors, like temperature readings from a weather station.
Okay.
Sliding windows can help you find periods where things are out of the ordinary, like a sudden spike or a drop that might signal a problem.
So if the temperature's pretty stable within a certain range, that's normal.
Yeah.
But if it suddenly jumps or plummets within our window, we might need to check things out.
Precisely.
This is making a lot of sense. So from stock prices to weather patterns, we're seeing the versatility of sliding windows.
And it goes even further. Sliding windows are used in image processing for things like object detection, where the window scans an image looking for specific objects or patterns within that window.
That's so cool. So from finance to weather forecasting to recognizing objects in images,
Yeah.
it seems like sliding windows are like the Swiss Army knife of data analysis.
That's a great analogy. It's all about understanding the patterns in a problem and then figuring out how to tweak that sliding window or line sweep to fit the situation.
This has been a really fascinating exploration so far. But I can't help but wonder, can we take these techniques even further? Are there ways to make them even more powerful or efficient?
Definitely. We've covered the fundamentals of sliding windows and line sweep, but there's a whole world of optimizations and advanced techniques out there. For example, remember when we used a DEEC to find the maximum value in a sliding window?
Yeah, that was a clever way to solve that problem.
It was. But for very large data sets, or if we need super fast processing, there's another data structure that might be even more efficient. The binary heap.
Okay, binary heaps, those are a bit more advanced.
They are.
They're like those tree structures that help you quickly find the smallest or largest element in a set.
Exactly. And by using a binary heap, specifically a max heap in this case, we can keep our Windows elements sorted even faster compared to a deck.
So it's like upgrading our leaderboard
Yeah,
to a supercharged, optimized version.
exactly.
That's amazing.
Yeah.
Are binary heaps the only trick up our sleeve for making things more efficient?
Oh, not at all. There are other specialized data structures and algorithms, like segment trees and Fenwick trees, that can be really powerful when combined with sliding windows.
Wow, this is getting seriously high level.
It is. But that's what makes this field so exciting. There's always something new to learn, a new technique to master, always room for improvement.
I'm really feeling motivated to start experimenting with these ideas. But before we get lost in the code, you mentioned a connection between sliding windows and dynamic programming earlier.
Yes.
How do those two concepts relate to each other?
That's a great question. It leads to an area where these two techniques actually intersect. Dynamic programming, it's all about breaking down a problem into smaller, overlapping subproblems, and then saving those solutions to avoid doing extra work.
Right, so it's about being smart and efficient with our calculations.
Exactly. And often, sliding windows can be a stepping stone to a dynamic programming solution.
Okay.
The way sliding windows let us focus on those smaller subproblems lines up really well with the whole dynamic programming approach.
I'm starting to see the connection. But could you give me a specific example of how they work together?
Sure. Think about the classic problem of finding the longest increasing subsequence within an array of numbers.
Longest increasing subsequence.
Yeah,
So we're looking for the longest sequence of numbers where they're always getting bigger.
exactly. And traditionally, this is solved with dynamic programming, where you build up a table to keep track of the length of those increasing subsequences.
Yeah.
But we can also approach it using our sliding window. Imagine the window represents the current increasing subsequence we're working with.
Okay, so instead of a fixed size window, it grows and shrinks based on whether the numbers we encounter continue the increasing pattern.
Precisely. As we slide along, we add numbers to our subsequence as long as they're bigger than the last one in the window. If we hit a number that breaks the pattern, we adjust our window, either shrinking it or shifting it to start building a new subsequence.
So our window is like this dynamic container, always capturing the best increasing subsequence we've seen so far.
Exactly.
And if we keep track of the maximum size that window ever reaches, we'll know the length of the longest increasing subsequence in the entire array.
You got it. It's this really cool interplay between sliding windows and dynamic programming. Sliding windows provide that intuitive way to break things down into smaller pieces,
Right.
while dynamic programming helps us store and reuse those solutions so we don't have to repeat calculations.
This is amazing. It's like sliding windows are the entry point to the powerful world of dynamic programming.
It kinda is.
I love how these techniques aren't just isolated tools. They're interconnected and can work together in really cool ways.
Exactly, and that's what makes algorithms so interesting. There's always something new to discover, more connections to make, and better ways to solve these puzzles.
This has been such a cool deep dive. We've covered a lot, from the basics of sliding windows to line sweep, and now even a bit of dynamic programming. But before we jump into code, I have one more question for you.
Okay.
What about machine learning? You mentioned a connection there earlier.
Yeah.
How do sliding windows fit into that world?
That's a great question, and it leads us to a really interesting area. Machine learning might seem complex, but the ideas behind sliding windows are still super relevant, especially when you're dealing with data that's constantly changing, not just static strings or arrays.
Real-time data.
Exactly. So how do sliding windows fit into this picture? Well, imagine you're building a model to predict stock prices, for instance. Instead of feeding the entire history of prices to your model all at once, you can use sliding windows to create these smaller chunks of data for the model to learn from.
Okay.
This helps the model capture those short-term trends and patterns that might be missed if we just looked at everything at once.
So it's like training the model to recognize patterns within specific time frames, kind of like giving it a moving spotlight to focus on different periods of market behavior.
Exactly. And this idea of analyzing data in chunks, it works really well in other machine learning applications too, especially with those real-time data streams you mentioned.
Like real-time data streams, what kind of scenarios are we talking about?
Well, imagine you're monitoring sensor data from a factory. There's all this information about temperature, pressure, vibration constantly coming in. We can use sliding windows to analyze that stream in real time.
Okay.
Looking for anything unusual that might be a sign of a problem?
So we don't have to wait for a ton of data to pile up.
Exactly.
We can just keep scanning as the data comes in, right?
Exactly. And it's not just about spotting problems. Sliding windows can be used for things like sentiment analysis on social media. Imagine a window sliding over tweets to see how people feel about a topic.
So we're tracking how people are feeling in real time just by looking at what they're posting online.
That's a great way to think about it. And using sliding windows in these situations, it means we can handle all that data without getting totally overwhelmed.
This is really eye-opening. Sliding windows aren't just for specific algorithm problems, are they? It seems like they're a fundamental concept that pops up in all sorts of fields.
They are. And the more you explore this idea, the more connections you'll find. Being able to break down problems into smaller, more manageable parts, it's a skill that goes beyond just programming. It's useful for anyone working with data, whether you're a programmer, a data scientist, or just trying to make sense of things in your own life.
This deep dive has been amazing. We started with sliding windows and went all the way to line sweep, dynamic programming, and now even machine learning. It feels like we've gone on a wild adventure.
I agree. It's been a fun journey.
But before we wrap up, one last question. What's next for sliding windows? Are there any exciting developments or new areas of research you're keeping an eye on?
Oh, absolutely. The world of algorithms and data analysis is always changing. There's always something new and exciting to discover. One area I find particularly fascinating is the combination of sliding windows with deep learning.
Deep learning, that sounds pretty intense.
Yeah. It can be, but the core ideas behind sliding windows still hold true, even in that context. Researchers are finding ways to use sliding windows within deep learning models to help them process data that comes in a sequence, like time series data or even text.
So we're applying this concept of a moving window to the very way these models learn and understand information.
Exactly.
That's pretty incredible.
It is, and it's opening up new possibilities in areas like natural language processing, speech recognition, even analyzing videos. Being able to handle sequential data efficiently is super important in those fields.
This is really exciting. It feels like sliding windows are not just some old technique. They're a crucial part of the future of data analysis and artificial intelligence.
You've got it. And that's what makes working in this field so rewarding. There's always more to learn, more to explore, and new ways to push the boundaries of what we can do.
Well, on that inspiring note, I think it's time to wrap up this fantastic deep dive.
I agree.
Thank you so much for sharing your expertise with us today. It's been a truly incredible journey.
It's been my pleasure. And to everyone listening, we hope you've enjoyed this exploration of sliding windows. Keep experimenting, keep learning, and see what you can achieve with these powerful techniques.
All right, we're back, ready to wrap up our deep dive into sliding windows. It's been quite a journey, from those basic string manipulations to line sweep techniques, even touching on dynamic programming. But you saved the most interesting connection for our last, sliding windows and machine learning. Honestly, that's a field I've always found a bit mysterious.
It definitely captures the imagination. But even though machine learning can seem complex, those core ideas behind sliding windows are still relevant. Think about how sliding windows help us break down data into chunks, finding patterns,
Right.
and making decisions based on that smaller view.
It's like having that moving lens so we don't get overwhelmed by the whole picture.
Exactly. And that approach is super useful in machine learning, especially when you're dealing with things that change over time, like time series data or real-time data streams.
Okay, now we're not talking about static strings and arrays anymore.
That's right.
We're talking about data that's constantly evolving.
Yeah.
So how do sliding windows fit into that?
Let's say you're trying to predict stock prices. Instead of giving your model all the historical price data at once, you could use sliding windows to create smaller chunks of that time series data.
Okay.
This way, the model can learn from those specific windows, finding short-term trends and fluctuations it might miss if we looked at everything at once.
So it's like we're training the model to see patterns in those focused timeframes.
Yeah,
Almost like we're giving it a moving spotlight to examine different periods.
exactly. And this idea of looking at data in chunks works in other machine learning applications too, especially when you have those real-time data streams.
Real-time data streams?
Yeah.
That sounds pretty intense. What kind of scenarios are we talking about there?
Well, think about monitoring sensors in a factory. You have this constant stream of data, temperature, pressure, vibration coming in all the time. Using sliding windows, we can analyze that stream as it happens, looking for anything unusual that might be a sign of a problem.
So we're not waiting for a ton of data to build up before we can do anything.
Exactly.
We're always on the lookout for insights, right?
You got it. And it's not just about finding problems. Sliding windows can also be used for sentiment analysis in social media. Imagine a window moving over tweets to see how people are feeling about a specific topic.
So we're tracking the overall sentiment as it changes in real time, just based on what people are saying online.
That's a great way to put it. And by using sliding windows, we can handle huge amounts of data without getting swamped.
This is incredible. So sliding windows aren't just for specific algorithm problems. They're a core concept that pops up all over the place, even in cutting-edge fields like machine learning.
You're absolutely right. The more you explore this idea, the more connections you'll find.
I'm definitely seeing that.
And that ability to break things down into smaller pieces,
Mhm.
to analyze them efficiently, it's not just a programming skill. It's valuable for anyone working with data, whether you're writing code, analyzing information, or even just trying to make sense of the world around you.
This has been an amazing deep dive. We started with the basics of sliding windows and ended up exploring their applications in everything from string manipulation to line sweep, dynamic programming, and now machine learning. It's been an eye-opening journey.
I agree.
I feel like I've got a whole new way of looking at problem solving.
I'm glad to hear that. And remember, this is just the start. The more you practice, the better you'll get at using these techniques.
And I'm definitely feeling inspired to dive into some coding challenges. But before we wrap up completely, one final question. What's next for sliding windows? Anything exciting on the horizon? Any research you're particularly interested in?
That's a great question. This field is constantly moving forward, so there's always something new. One area that I find really fascinating is the combination of sliding windows with deep learning.
Deep learning, that sounds intense.
It is a complex area, but the basic ideas behind sliding windows are still relevant. Researchers are looking at ways to use sliding windows within those deep learning models to help them process data that comes in a sequence, like time series or even text.
So we're taking that idea of a moving window and applying it to the very structure of how these deep learning models work.
Exactly.
That's amazing.
It is, and it could lead to breakthroughs in natural language processing, speech recognition, even video analysis. Being able to handle sequential data efficiently is crucial in those areas, and sliding windows are proving to be a really valuable tool for that.
This is so cool. It feels like sliding windows aren't just a technique from the past. They're going to be a big part of the future of data analysis and AI.
I think you're right, and that's what makes this field so exciting. There's always more to discover, more to learn, always new ways to push the boundaries.
Well, on that inspiring note, I think it's time to wrap up this fantastic deep dive. Thank you so much for sharing your expertise with us today.
It's been my pleasure.
And to everyone listening, thanks for joining us. We hope you've enjoyed this deep dive into sliding windows. Keep experimenting, keep learning, and see what you can achieve with these powerful techniques.
Absolutely.